Hello everyone, I am Dr. Shweta Sharma, a postdoctoral researcher working in Dr. Priya's research group at Penn State. Today I will be talking about piezoelectric thin films. So this will be the outline of my talk today. First, I will introduce what piezoelectric effect is and its origins. Then I'll talk about common piezoelectric materials and their applications. And then I will talk about the techniques that are used for growth of these piezoelectric thin films. And finally, I will show one design for piezoelectric thin film based energy harvester. So what is piezoelectric effect? It is the ability of certain materials to generate voltage in response to applied mechanical stress. Piezoelectric effect is a reversible process. It has like direct and converse effect, which means that when you talk about direct effect, it means that the material generates electricity when the stress is applied to it, and conversely, it's that the mechanical stress, basically the material generates stress when electric field is applied to it. So talking about history of piezoelectric materials or the piezoelectric effect, it was first observed in 1880 by the brothers Pierre and Jacques Curie using crystals of Rochelle salt and quartz. And there are several advantages of this piezoelectric effect. First is that it is very useful for low voltage and low power application based devices. And these devices are very lightweight and smaller in sizes. Also, these are self-sufficient and they do not require any such maintenance from reliable power sources. And they have high conversion efficiency. So talking about the origin of piezoelectricity, this slide explains the origin using quartz as the example. So the piezoelectric effect originates by redistribution of electric charges within certain materials when they undergo mechanical stress. Now the question arises, can all materials be piezoelectric? And the answer would be no. Only the materials that show lack of center of inversion symmetry, or which are also known as non-centrosymmetric structures, only these can be piezoelectric. Now what it means? So consider this arrangement of positive and negative charges inside a material in equilibrium state, like when there is no force applied to it. In such case, there will be no net charges or no net dipole moments because all the charges are equal and opposite and they are cancelling out each other. When such material is subjected to like deformation, say when this material is compressed, then these charges will start redistributing within the material, and it will happen in such a way that there will be net dipole moment formed in certain direction. If you do the opposite, like when you will stretch the same material, like in this third case, then again there will be a net dipole moment generation because of the redistribution of charges, but the direction will be reversed. So whenever there is a dipole moment formation, that means it leads to piezoelectricity. Now coming to materials which have centrosymmetric structure, you see that in all the cases, whether the material is in equilibrium or when it is subjected to deformation, in all these cases, the charges will get rearranged in certain manner that there will be no net dipole moment. It will always be equal to 0. And in such cases, you will see that there will be no piezoelectric effect observed. So the common types of piezoelectric materials can be classified into two main classes or based on their structure. So the first one is woodside structure, and the examples of such materials are non-ferroelectric materials like zinc oxide and aluminum nitride. These materials have low piezoelectric coupling coefficient, but still they are very common for use in resonator applications. The other class is the perovskite structures, and which can be lead-based materials like PZT or lead-free materials like potassium sodium niobate, BNT, and BFO. So all these materials have their own advantages and disadvantages. Like this lead-based material is having high piezoelectric coefficient, but their use is limited because it contains toxic element lead in them. So this here diagram shows the basic perovskite structure, how it looks like. So it is a basic APO3 kind of structure with lead atoms for PZT. The lead atoms are arranged at the corner sides, the oxygen atoms are arranged at the face centers, and the titanium and zirconia are at the body center. Also, these perovskite structures are ferroelectric in nature up to a certain temperature, which is called Curie temperature, TC. So for temperatures up to TC, you see that the structure is arranged in such a way that there is a formation of non-heterosymmetric behavior, and there is a direction of polarization in such case. And because of that, you see that only up to TC, there will be a piezoelectric effect of ferroelectricity observed. However, when you go beyond this temperature, TC, the structure is no longer non-centrosymmetric, it becomes centrosymmetric, and you then do not observe any ferroelectric behavior, it becomes paraelectric. Coming to the question why thin films are preferred over bulk materials. So again, there are several advantages for this. And the first being that we require very low driving voltages for thin films. What it means is, like, for getting the same response or output out of a thin film, you will require much smaller voltage in comparison to the bulk material. These are also, they provide flexibility and have high performance. And also because of their size, they allow for miniaturization, and it is possible to scale them up, and because of this, it leads to cost effectiveness. So these piezoelectric thin films can be used for several applications, including energy harvester device, wearable devices, implantable devices, and implantable devices can only be used with materials that are non-toxic in nature, such as potassium sodium niobate. Then these materials are used for sensor applications and also in MEMS and nano devices. So the techniques that are used for depositing these piezoelectric thin films can be physical vapor deposition technique as well as the chemical deposition technique. In physical, we have again several options like sputtering, pulsed laser deposition, evaporation method. And in chemical technique, we have like liquid phase methods such as sol gel and spin coating. And the other is the vapor phase, which is called chemical vapor deposition. So each technique has its own advantages and disadvantages. And based on our application, we decide what technique we will be using it for. So here I show one of the techniques and how piezoelectric thin films are grown using pulsed laser deposition technique, which is a physical vapor deposition method. So this is the schematic of the PLD system. So the material, the ceramic material of the piezoelectric ceramic material is kept in form of a pellet inside the vacuum chamber. And the vacuum is normally a very high vacuum order, around 10⁻⁻⁶ torr. And the substrate is kept just opposite to the target. And then a very high pulsed laser beam is entered into the system such that it starts ablating the target material. And when this happens, then the atoms from the target get transferred to the substrate. So during this process, there is a formation of localized plume over the target material, and whose photo you can see here. And there can be various parameters that you can vary during deposition to like find out or like get the maximum performing thin film out of it. So you can change like the gas ambience, like whether you want to use or argon or oxygen based on the thin film that you require, the pressure of the gas, the substrate temperature, target to substrate distance. All these parameters play an important role in making thin films. And because of these changes in the parameters, the crystallinity, the morphology of the thin film can change. So once you deposit thin film using, say, PLD technique or any other technique, you have to characterize it for different parameters before using it in applications. So by that, I mean, you need to measure its piezoelectric coefficient, electromechanical coupling, the Curie temperature, the dielectric properties, the ferroelectric properties. And all these parameters are important to characterize the quality of the piezoelectric thin film. So once you have, say, the maximum performance thin film grown, Now you want to use it for certain applications. So I will talk about how you can make a piezoelectric thin film energy harvester. So this is the typical construction of a piezoelectric EH, where you are making this device on a silicon cantilever kind of structure. So cantilever is because it is fixed at one end and the other end is kind of free to vibrate. So over this silicon cantilever, what you are doing is you are depositing a bottom electrode of chrome gold, and in between you are making this piezoelectric thin film of PZT, and then you have a top electrode of chrome gold again. So it's basically a MIM, metal insulator metal structure over a cantilever, and then you also have a proof mass for the vibrations. So this is the experimental setup for measuring the output voltage and power. So it consists of the cantilever, which is clamped with a piezo shaker, and this piezo shaker is connected to the function generator to actuate by frequency. And then using a load resistance, you also connect the two electrodes to an oscilloscope to measure the output voltage generated. So the mechanism that is followed is like this. So first you externally excite this cantilever structure, and when this external excitation happens, this induces mechanical vibration into your piezoelectric thin film system. And because of that, the piezoelectric effect arises due to redistribution of charges, and this leads to the output electrical voltage, which you can measure in terms of voltage and then convert it to power. So these are the typical output responses that you can record out of this like energy harvesting cantilever system. So here it shows that with change of frequency of this actuation, you will find that at a particular frequency, your cantilever resonates maximum, and because of that, it generates maximum voltage. And also by tuning this load resistance, you can find out the maximum output power. So this was all about it, and thank you.